Hey guys, um, happy Friday. Uh, so today I wanted to pick up where we left off, talking about degenerate perturbation theory. So last time we laid out the formalism, talked about how or why we have to change things up a little bit when we run into degeneracies. Um, and we basically came up with a plan or a recipe, if you will. And that was when you identify. So the first thing you have to do is identify if there are degenerate states in the problem that you're trying to solve. If there are, then you want to construct the matrix, the Hamiltonian matrix for that subspace, so they're not guaranteed that there's always going to be all the states are degenerate. There might just be some particular states that are, and that's usually the case actually. So you first thing you do is identify the degenerate space or subspace of your problem, and you construct that matrix. And then from there, it's just kind of turning the crank. So you diagonalize that matrix, right? And you diagonalize it just like you would when you're solving for eigenvalues. So in this case, it's called the secular equation, but it's the same idea. So you diagonalize the matrix, you find the eigenvalues, plug those back in, and get your new eigenkets, right? So it turns out that the roots of that secular equation, like we showed last time, are actually the first order energy shifts, right? So they're the values that you'll add to that, the zeroth order energy, the energy that all these states share, and you know, depending on how many distinct eigenvalues you have, that degenerate state's going to split into some non-degenerate states. Uh, And the base kets that you get from diagonalizing, or the base kets that do diagonalize the perturbation matrix, are now what we call the correct zeroth order kets, right? So they're the linear combinations of the original zeroth order kets. Okay, so that's where we left off. And today, what I want to do is work through a couple of examples. But before I do that, I want to take you down the perturbation path. Okay, so this is a kind of, I don't remember what these diagrams are called, but they're I made this up a couple of years ago just to help people understand, like, when to use perturbation theory, or what type of perturbation theory to use. So it starts out in this diagonal, right? And the first thing you ask is the Schrodinger equation exactly solvable? And if it is, great. You go back and look at quantum one notes to figure out how to solve the problem, right? If it's not, then you have a couple choices, right? We've already seen that you can go and try to guess a wave function, right, and try to solve the problem that way, and that's called the variational method. So that would be one path that's not shown here, right? So in the case where the Schrodinger equation is not exactly solvable, but we can split it into a simple piece that we do know the solution for, plus a small piece that we can use as a perturbation, then we can use perturbation theory. Okay. So then once you establish that you want to use perturbation theory, you'll do this, as at an energy level by energy level kind of basis. And you'll ask yourself first, is the energy level that I'm working on, is it degenerate, right? Are there more than one state that have the same energy eigenvalue, right? If there's not, then you're golden, and you can go off and apply non-degenerate perturbation theory that we learned about last week, and you can go off and you can compute, say, the first order energy eigen shifts, right, which are just the diagonal matrix elements of the perturbation matrix in the unperturbed eigenbasis, right? And then the perturbed eigenkets, first order, are given by this formula, right? And so you're good to go, right? But if you have degeneracies, then that's when you have to apply this this kind of algorithm or recipe that we were just talking about, where you construct the Hamiltonian matrix, the sub matrix, a part of the Hamiltonian matrix that's degenerate, and then you have to diagonalize that, right? So once you diagonalize it, that we identify the eigenvalues of that matrix as the first order energy shifts, and the eigenkets that we get from diagonalizing the matrix give us the new zeroth order unperturbed states. Okay, so that's kind of the path of how to decide what type of perturbation theory do I apply. Okay, we'll see later on that one of the other questions that you'll ask is, does the perturbation depend on time? If it does, then you go off and do time-dependent perturbation theory. Okay, so the first example I want to consider is a particle in a 3D box. So this is a three-dimensional cube, okay? So inside the box, the potential is 0, right? And outside, the potential is infinite, okay? And so hopefully you look at this problem and you guys have seen this enough that you can just write down the solution, right? When I see the boundaries are between 0 and A in all three directions, I should be able to write down the three-dimensional wave function. It's just the one-dimensional wave function, three versions of it glued together, right? And so I get three sine functions, and I know there's a typo right here. This should be n sub z, but each of these guys should have their own quantum numbers, nx, ny, and nz, right? And we should know what the solutions are, and we should know what the normalization is, okay? All right, so we know what that is, right? And so the wave functions get glued together, the energies get summed together, right? So the zeroth order eigenvalues, or the energies, are going to be this factor out in front, and then a sum of nx squared plus ny squared plus nz squared. Okay, so it's just summing up the three different energy eigenvalues in the three different dimensions, right? Okay, so now what I want to do is introduce a perturbation, okay? And I'm only going to introduce a perturbation in part of the box, okay? This is starting to sound like a magic trick, but it's not. It's a perturbation theory, okay? So we're going to introduce a perturbation. It's a constant perturbation, so that's why I call it V naught, okay? So it's independent of any time or space or anything like that. But I'm only introducing it in part of the box, right? And actually, I'm only introducing it in 1/4 of the box, right? If you think of in terms of volume, right? So it's between 0 and a over 2 for both x and y. Excuse me, but it goes all the way up, covers all of z. Okay, so try to if you're confused about this, stop the I almost said tape, but that's not tape. Stop the video and draw a picture, right? And understand where this potential is. Okay. So hopefully you're back and you drew a picture and now you totally understand this. Okay, so let's try to compute the energy shifts and the new eigenfunctions for the ground. We're going to do it for the ground state and the first excited state. Okay, so the ground state, first we're going to ask ourselves, is the ground state degenerate, right? Well, the ground state is the state with nx, ny, and nz all equal to 1, right? That's as low as we can go in all three. And so that would give us this energy eigenvalue, the ground state, unperturbed energy eigenvalue. And we see that it's not degenerate, right? There's only one state that corresponds to the ground state, okay? So that means that we can apply non-degenerate perturbation theory to it, okay? So I can go ahead and compute the first order energy shift by just computing the matrix element of our perturbation between the two ground state, between two ground state wave functions, right? And so that's what this is. So these should be sine squareds, right? Yeah. So these should be, this is another typo. So these should be sine squareds, right? Because I'm multiplying two wave functions together. And notice that I'm only integrating over the part of the box where the perturbation is, right? So in the x and the y integration, I'm integrating from 0 to a over 2, okay? And in the z, I integrate over the full length. Okay, so I can do that using Mathematica or whatever, or looking up in a table, and I get something that looks like this, right? And when I multiply all this stuff out, so this is the first order energy shift, I see that the first order energy shift goes like V naught over 4, okay? And it kind of makes sense physically because, you know, we've raised the potential by a constant amount, V naught, in a quarter of the box, okay? So it makes sense that we get this factor of 1 over 4. Okay, so that's it for the ground state. I just want to compute the corrections to the energy. So now what about the first order? Or what about the first excited state, right? Is the first excited state degenerate, right? So the first excited state would be the one where one of these guys changes to 2, right? So I could have 2, 1, 1, or 1, 2, 1, or 1, 1, 2. All right, so that sounds like we have degenerate states, and in fact we do. It's a threefold degeneracy, okay? So it's 3 distinct states that have the same energy eigenvalue, okay? So there is a degeneracy here, and it's threefold. Okay, so that means that we're going to have to apply degenerate perturbation theory, and the first step is to construct the perturbation matrix, right, for this first excited state. Okay, so if I have a threefold degeneracy, what are going to be we have to construct the matrix. What's the dimensions of this matrix? That's right, it's 3 by 3. Okay, so it's a 3 by 3 matrix, right? And we're going to want to diagonalize that. Okay, so I'm going to introduce some shorthand notation. So I'm going to call psi A the 1, 1, 2 state, psi B the 1, 2, 1 state, and psi C the 2, 1, 1 state. Okay, so then I want to construct this 3 by 3 matrix by sandwiching the perturbation between the wave functions, right? So here are the diagonals. I have AA, BB, and CC, and here I have AB and BA and CA and AC, and so on and so forth, okay? So what I want to do is go through and compute those matrix elements, where those matrix elements take this form, right? Something similar to this, okay? And when I do that, I find that 4 of these guys vanish, okay? And what else do I find? And I find that the others take these values, right? So I get these V naught over 4, constant piece coming out. And then kappa, I've just some numeric factor that comes out of the integration, 64 over 9 pi squared, okay? And I didn't want to have to keep writing 64 over 9 pi squared, so I just called it kappa. All right, so we've constructed our degenerate perturbation matrix, okay? And now we want to try to diagonalize this, right? We want to try to solve the secular equation. Okay, so I need to take our matrix and subtract off the identity being multiplied by some number, by some eigenvalues. You know, these are the guys that we want to find. Okay, so at this point, when I do this, a lot of you, and myself included, you see something like this, and you might want to just go ahead and factor out this V naught over 4. Okay, and that's fine. And most people do it correctly, but a lot of times what I see is that people factor this out and then go down here and compute this determinant, and they forget about that factor that's out in front. Okay, and then that throws the answer off. The units aren't right, and all hell breaks loose. So don't forget. So what I do is, it might be messy. I just keep the factors inside the matrix, because that way I'm not going to screw it up. Okay, so what we have is the determinant of this thing, right? And when I compute the determinant, I'm going to get some polynomial equation, right? And I can solve that polynomial equation. And what I end up finding is that I get the eigenvalues being V naught over 4, V naught over 4, 1 plus kappa, and V naught over 4, 1 minus kappa, right? And so these these are our first order energy shifts, right? So these are the values that we would add to whatever the whatever the unperturbed energy is, this guy. Okay. So you see that we started with three distinct states that have the same energy. And now we're going to have, once we applied this perturbation, we've fully lifted that degeneracy, right? And you can see that, so one state will be added by this, one will be like this, and one will have 1 minus kappa, okay? So this is a case where we fully lifted uh, this degeneracy, okay? And if you want to think of it on a higher level, I mean, before we introduced the perturbation, we had a threefold, or we had a symmetry, right? We had symmetry, three-dimensional symmetry, right? And so that led to the threefold degeneracy. But when we introduced this perturbation, we disrupted that symmetry, and so we disrupted the degeneracy and actually fully lifted it. Okay, so now we can take these guys, if we want to know what the new zeroth order eigenkets are, we can take these guys and feed them back in one by one into the original matrix equation, right, and solve it. And what I find is that my new eigenstates, I have one that stays the same, right? So this psi 2 is what I called psi A before, right? And psi A is the one that has the excitation in the z direction, okay? So that makes sense. I mean, because we haven't done anything to disrupt the symmetry in the z direction, right? So the eigenket that that corresponds to the excitation in that direction, in the z direction, it makes sense that it doesn't change. The other two, however, the ones that are where the excitations are in the x and y directions, those we have disrupted because our symmetry has chosen, a particular direction, if you will. And so what we find is that our two of the new states are kind of admixtures of these excited, the states where the 1, 2, 1 and the 2, 1, 1 have mixed. Okay. All right. So that's a simple example of degenerate perturbation theory. All right. And so what I want to do is cover one more example. Okay. So we're going to go back to our old friend, the hydrogen atom, and an external uniform electric field. Right. And you remember we did this probably about a week ago for the ground state, right? And we computed the energy shift, right, due to this electric field, and we found that it was second order in the electric field, and so this thing is called the quadratic Stark. That was called the quadratic Stark effect. Okay, so what I want to do today is look at the first excited state. Okay, and so the first question we want to ask is, do we have any degeneracies, right, for excited states? Well, we know that the hydrogen atom is characterized by three quantum numbers, NLM, right? N being the energy, L being the L squared quantum number, and M being the LZ quantum number, right? Where L we know runs from 0 up to N minus 1, right? And M runs from minus L to plus L in integer values, right? Or different, the difference being integers. And so the degeneracy is going to be 2L plus 1 coming from the M, and then we sum over all values of L. And we've shown this before, that the degeneracy of the hydrogen atom, a particular energy level, goes like N squared. Okay, so the hydrogen atom is a highly degenerate system once you get beyond the ground state. Okay, so the ground state, like I said, was non-degenerate, so we could apply non-degenerate perturbation theory, and we did that last week. It's called the quadratic Stark effect, and so we found that this thing went like E squared, right? So E here is the electric field. Okay, so let's look at the first excited state now. So the first excited state is going to be N equals 2. All right, so that means that I'm going to have L equals 0 or L equals 1. Okay, so if I have L equals 0, then the only possible value of M is 0. But if I have L equals 1, then the possible values of M are 0, minus 1, and plus 1. Okay, and so what I see is that I have four states that have the same energy. Right, so I have a four-fold degeneracy. And if I look, if I go back and look at what we had before, or what we found in general, that the degeneracy of the hydrogen atom goes like n squared, so it makes sense. All right, so we have a fourfold degeneracy, and we can compute the unperturbed energy. We know the formula for that. All right, so now let's introduce our perturbation. Okay, so we're going to turn on this uniform electric field, and we're going to point it in the z direction. Okay, and here we're considering where E is a weak field. All right, so it is a perturbation. It's not the dominant piece of the Hamiltonian. Okay, the Coulomb potential it takes care of that. Right, so this is a repeat of what I just said, the quadratic Stark effect. Okay, so the first excited state, you've seen it's fourfold degenerate, right? So that means that the perturbation matrix we construct is going to be, what are going to be the dimensions of it? That's right, 4 by 4, and it's a mess. Okay, so we have a 4 by 4 matrix. We're reforming these matrix elements, and we're plugging in here for the perturbation, our electric field, and the Z. Basically it's the Z operator that gets plugged in here, right? And they're sandwiched between hydrogen atom wave functions for the first excited state. Okay, so it looks messy, right? But there are some things before you go off, crazy willy-nilly and start computing stuff. There are a couple things that you can do to simplify your life, right? So first you say, oh my God, I have to compute 16 of these matrix elements. But no, we know that's not the case because the Hamiltonian has to be Hermitian, right? And so that means that there's only, and I put only in air quotes, or quotes here because it was funny to me, that there's only 10 independent. Okay, so we've gone from 16 down to 10, right? However, we know that we learned a couple lectures ago that the Z operator is odd under parity, and these hydrogen atom states have definite parity, and so the Z can only connect odd with even states, right? Or if you want to talk about it in terms of what was the name of that theorem? I just forgot it. The tensor theorem, the Wigner-Eckhart theorem, right? Then you know that the only non-zero matrix elements are going to be the ones where L prime differs from L by plus or minus 1, and M prime is equal to M, right? And so that means that, when you go through them and you check all the different possibilities, that the only non-zero matrix elements are this guy, 2, 0, 0, 2, 1, 0, and 2, 1, 0, 2, 0, 0, right? But these are just complex conjugates of each other, okay? And so now what we can do is first compute the matrix element, and then we'll plug it in the matrix and then diagonalize the matrix, okay? So the matrix element looks like this, right? And I plug in my perturbation, the minus little e times big E can be pulled out. So it's a matrix element for Z, right? And we can calculate this guy, right? And so we ended up with something like this, right? And what is that? I don't understand. I don't know what this really means here. I'm just saying that it's equal to the complex conjugate, right? Because it's real, so it's the same for both. All right, so when I construct this Hamiltonian matrix, it's pretty sparse, right? There's only 2 non-zero values, right? And in fact, if I want to diagonalize this, I can just focus on this 2 by 2 sector up here, right? And so I compute the secular equation, or try to solve the secular equation for this little submatrix up here. And I can read off the eigenvalues. They're going to be plus or minus 3 times the Bohr radius times electric charge times the electric field, right? And what you see is that, so these are the first order energy shifts, okay? So we have a 4-fold degeneracy and we get 2 non-zero eigenvalues. So we're only partially lifting the symmetry this time, right? And the first thing you notice is that this thing is linear in the electric field, whereas before we found that for the ground state, the first order energy shifts were quadratic. Here they're linear. So this is called the linear Stark effect. Okay. And you can go through, you can also compute the eigenkets, the new eigenkets. And again, those are easy because this is basically a 2x2 matrix, right? 2 of these guys stay the same, right? So remember, that's what I was saying, that we had a 4-fold degeneracy, and we only got 2 non-zero eigenvalues out of the secular equation. So it's telling us that we only partially lifted it, right? And so what happens is the states that are associated with this kind of block of the Hamiltonian are the guys that mix, right? So I get 2 new states. I call them plus and minus, call them whatever you want, but they're admixtures of the m equals 0 states. Okay, so these are the kets that diagonalize the Hamiltonian, right? So just some quick notes. Again, we see that in this case, the perturbation only partially lifted the degeneracy, and a lot of times that will be the case, right? So we didn't completely destroy the symmetry here. Here we have spherical symmetry, right? And we're applying the electric field in the z direction, so we would expect the m equals 0 states to be the ones that are affected, right? And we should have, like I said, should have expected this, since the perturbation matrix or the perturbation Hamiltonian goes like z. Right? And now what we see is that the new 0th order kets are not necessarily parity eigenstates, right? Because now these guys are admixtures of L equals 0 and L equals 1. And remember, the parity goes like minus 1 to the L. Right? So therefore, they're allowed to have a non-vanishing electric dipole moment. Right? And that's an important physical effect, right? Of the hydrogen atom and of other atoms and other fundamental type particles. And so that's what gives rise to this effect, this linear effect from the electric field. Okay. All right. So that's where I'm going to stop today. We'll pick it up next time. I can't remember what we do next, but it'll be fun. So I don't know. I think maybe the homework's due tomorrow. I'm not sure, but get it in when you can. If you have questions, write me. Remember to always write to my Gmail account, because I'm very bad about checking the UTA one. All right. So have a good weekend, and I'll see you next week. All right. Bye.